Hello, everyone, for joining. Uh, okay, so today we are going to discuss problems from week 11, assignment week 11. Okay, I will explain the solutions, a few solutions, and then if you have any doubt, you can stop me and ask any question. Okay, good evening. Okay, so question number one. So today's session will cover topics about totally boundedness, okay, and compactness. It will use a theorem which classifies the uh, compact spaces compact subspaces of metric space. Okay, so we will use that theorem in the first question, and then we will also see eq continuity. We will also talk about the topology convergence, one point wise convergent topology and uniform convergence topology. Okay, so let me start with question number one. So question number one is, which of the following implications hold for a journal metric space? Okay, first implication is that totally bounded implies compactness. Second is compact implies completeness. Third is complete implies compactness. And fourth is totally bounded and complete implies compactness. Okay, so as usual, I will wait for you guys to think about this and let me know the answer, whatever your guesses are, and then we will discuss the solution. Okay. Okay, so let me discuss the solution then, if there is no guess. So we have totally boundedness implying compactness. So let us first recall the definition of totally boundedness. We will go step by step. Okay, option D. Option D is correct, but there is another option that is also true. The Yeah. So let us first recall what is a totally boundedness. A subset A of the metric space xt is called totally bounded if for all, if for each r in real positive, there exist finitely many b r for each, let's say epsilon positive, that would be easier. There exists ball of epsilon radius covering a. Okay, so one, let's say this 1 to n. Okay, there exists finitely many balls covering the space n. This is a totally boundedness. So every compact set is totally bounded. That is, uh, every compact set is totally bounded. That is clear because you can cover them by, you can consider, you can take any radius ball cover, and then by compactness there exists a finite subcover. So that is trivial. There is nothing to prove. But here the question is asked about the converse part. Okay, so for that, let me first write down a theorem. And what is a complete space? What is a complete metric space or metric set? Metric space. Um, xt is complete if every Cauchy sequence converges. All right. And what is a Cauchy sequence? Cauchy sequence uh, is a sequence who such that they are, yeah. So for every epsilon, there exists a natural number n such that the distance between the xn and xm is smaller than epsilon for all um, nm larger than n. So the points of the sequence are getting closer and closer. That is what the Cauchy sequence is. Okay, this is different from the convergence sequence. For the convergence, you have a limit, so every point is getting closer to the limit point. But in this case, the points of the sequence are getting closer to each other. There's a difference. Okay. Uh, Now let me state the theorem that we are going to use in this. So this theorem is is a classification of compact spaces in a metric space, and partly it has been proved in the classification of compact spaces in a metric space. All right. So what is this theorem? This theorem says that um, let xt be a metric space, then following are equivalent. A is a totally bounded and complete is a compact set. Okay, there are more to it, but this equivalence has already been proven in the class. The other equivalence I'm not going to uh, prove or show. Okay, Mohana said that it's ABD. A is wrong, B and D are correct. Okay, so now let us see. So the option three, the other equivalents are not important as of now. So let us keep our classification result for this two statement. That means every compact set is every compact subset of X is implies that it is a totally bounded and complete space, and totally bounded and completeness together implies that set is a compact subset. Okay. Now let's come back to the question. So in the question, it is asked that totally bounded implies compactness. So totally bounded requires completeness in order to imply compactness. So this is not correct. But we need to come up with a example, okay, where this is not true. So this is we need to find out an example or a counter example to be precise. Okay. For option B, compactness implies completeness. This is because of the classification theorem that I just wrote. So this is true. So this is true. The completeness implies compactness. This is again not true. We need to again come up with a counter example. All right. And the totally boundedness and completeness implies compactness. That is already we have saw in the statement of the theorem. So this is true. So B and D are correct. A and C are not correct. Okay. Now let us do step by step analysis. So option A, which says that totally bounded implies compactness. For this, we need to come up with a counter example. All right. So consider this set X, or let's say this set A, which is the intersection of the interval with rationals. So it is precisely set of all rationals in the interval 0, 1. Now, now claim 1, A is a totally bounded set. Okay. How do we prove that it is a totally bounded set? It is simple to prove. You consider, so this is the proof of the claim 1. Consider a cover, consider a cover B epsilon X, okay, for each X in A. Okay. So you consider this cover. Let me write it as Q because elements in A are rationals. Okay. So Q is a better notation for a rational. Let me use Q. Consider cover by balls of epsilon radius. Okay. Of A. Now we know that Q is a dense set in R, implying that A is dense in 0 comma 1. Okay, in the subspace topology, because on 0 comma 1 interval we have the subspace topology. So whatever is the dense set on the in the bigger space, restriction to that, to the subset will in the to the subspace will be the dense set in that subspace. All right. So A is a dense set in this interval. Now once A is a dense set in the interval, um, all right. So the cover of B epsilon Q also covers the closed interval 0 comma 1. Why? So for that, take a point x in the interval. Now set A is a set dense subset of 0 comma 1 interval. So there exists Q in A such that B such that X is contained inside the epsilon neighborhood of that Q. Okay. If you cannot find out any such Q, then it is a contradiction to the fact that it is a dense set. All right. So this is because of the denseness. So this implies that uh, this cover covers the interval, and it is already known that the interval in R is a compact subset, and the reason being is the Henry-Borel theorem, which says that closed bounded R closed bounded subsets of R are compact subset. All right. Now using the compactness, given a cover of a compact subset, you can always find out a finite subcover. So thus there is a finite subcover of these balls centered at points in A. Okay, denote the denote balls in finite cover by B1 up to Bn. Okay, so union of Bi from 1 to n, it contains interval 0 comma 1, and interval 0 comma 1 contains the set of rationals in that interval, which is A. Okay, so we have found out balls of epsilon radius, uh, finite many balls of epsilon radius that covers A. Thus uh, therefore A is a totally bounded set. All right. So this completes the proof of claim 1, right? We have started claim 1 over here. So this is the proof of claim 1. It looks big, but it's not, because I've written down the ideas as well. So it is not that big. Okay. Now we need to prove that, which is our claim 2. A is not compact. Okay. Now we want to prove that A is not compact. Now for that, we use another equivalence definition of compactness, which says that which is in a metric space, compact sets and sequentially compact are equivalent. Okay. Now what is a sequentially compact? So if it is compact, then it implies that it is a sequentially compact. Sequen Sequentially compact. And now what is a sequentially compact? Sequentially compact means every sequence has a convergent subsequence. All right. So we need to find out uh, a sequence that does not have a convergent subsequence. All right. So then, if we can find out a sequence having no convergent subsequence, which this will imply that the set A is not sequentially compact. So it will also imply that it is not compact. So not sequentially compact implies that it is not compact. All right. And what is a sequence? What is a sequence? So now you need to think that what is A? A is set of rationals in your interval. Okay. So you just consider you just consider a sequence of rationals that converges to an irrational. Okay. So for example, you can think of E. So the Taylor expansion of E. So E is an irrational number, but the Taylor expansion of this consists of rational terms, right? So you can consider that sequence, or maybe you can consider E minus 1. So E minus 1 lies in 0 comma 1, or you can take E minus 2. If it doesn't, then you can take E minus 2, whatever suits you, and you consider the Taylor expansion of E minus 2, and you take the partial sums at each stage to be the sequence, and that converges to E minus 2. So sequence you get to be a rational sitting inside the interval, but the limit is a rational which is not part of the uh, rational in the interval. So it does not have any convergent subsequence in A. Okay, so it is not sequentially compact, implying that it is not compact. Okay, so this completes the argument for us that a totally bounded set is not a compact set in a metric, in a general metric space. All right. Now, 3. Option C. Option C says completeness implies compactness. Okay. So completeness does not imply compactness. And for example, you consider R. Okay. R with the usual Euclidean metric. All right. Is a complete metric space, right? But R is not a compact metric space. R is not compact. All right. So this is the example. This is a counter example for this assumption. If I so completeness does not imply compactness. All right. Okay. So this completes the solution of the first question. Only A, oh sorry, only B and D are correct. A and C are false. Okay. Any doubt in this solution?
Sir,
Yes.
claim 2 is also not compact. A is also not compact. Sorry,
Yes.
sorry. A is not complete.
A is not.
Complete. Complete.
Yeah. A is not complete. Rest.
Then it is not complete.
Ha. That is true. But here we are using sequentially compactness also. Compactness implies sequentially compact,
Okay.
which implies if it is not sequentially compact, then it is not. But completeness also, if you can, yeah, this is not the only proof. If you can prove that it is not complete, you have argument for that. That will also work because compactness implies completeness. So if it is
Yes.
not complete, it cannot be compact.
Yes.
That is true.
Anyway, suppose A take as any open interval
A,
and taken as open interval.
open interval. Okay.
Yes. Which is totally bounded but not compact. Example.
I don't get your question. Can you repeat your question?
Open interval A comma B is totally bounded. Open interval, any open interval.
Open interval a comma b is totally bounded. Okay.
With respect to standard metric.
Okay.
But not complete.
Okay.
Same argument I am using. Example, counter example.
Okay.
I just trying for that counter example.
Okay. Okay. Now let's move on to question number 2. It says that let X be a totally it's a totally bounded metric space and let Xn be a sequence in X which of the following are true. Option A, for each k naught in the natural numbers given any metric ball of radius 1 over k naught, we must have Xn in B naught. For each k naught in the natural number, there exists a ball, there exists an open metric ball, a B naught. It's better to write this much. So B naught of radius 1 over k naught. This is better. Such that Xn is in B naught. Okay, we must have Xn in B naught uh, for infinitely many. Okay, this is also for infinitely many. Option C. Uh, Option C says if for some k naught in the natural numbers, there exists B naught of 1 over k naught such that Xn is in B naught for infinitely many n, then for any k1 greater than k naught, k1 in natural number, there exists an open ball b1 of radius 1 over k1 such that xn is in b naught intersection b1 for infinitely many. Option D, there exists there exists a Cauchy sequence. Cauchy subsequence. All right. So this is the question. Again, I will give you a few minutes to think about it, and then we will discuss. Okay, let's discuss the solution. Um, so X is given to be a totally bounded metric space. X can be a sequence in which now we need to say which of the following are true. So for each k naught given a metric ball of radius 1 over k naught, we must be able to find out xn for infinitely many n. Okay. Okay, the B is correct. B is correct answer. That is true. But there is one more answer which is correct. So there are two more answers which are correct. C and D are also correct. Now let us see why A is not correct and B and C, D are correct. So A is not correct because it asks that given any metric ball, okay, given any metric ball, it needs to have infinitely many points of a sequence. So it is not possible because you can take a sequence to be, you can take a constant sequence, okay, and that constant sequence uh, is nothing but a point, okay, and that point will only lie in one ball only. It will not lie in any other ball, okay, or whatever radius you take. So in that case, A is not correct, so it is not true. Now for B, B is true because you will always be able to find out a ball in which the sequence is contained. Now let us see why. So X is totally bounded. So we consider, so X can be covered by a by finitely many balls of radius 1 over k naught. Okay, and now because sequence is part of, yes, so um, so now X is, now sequence xn is contained inside X and it is contained inside the union of the balls. So most of the, so infinitely many points of the sequence, infinitely many index elements of the sequence must be part of one of the ball, okay, at least one of the ball. So thus there is a ball bi containing xn for infinitely many. Okay, now why is that true? Because if there is no such ball that contains infinitely many xn's, then then it will not be a sequence, okay, it will be a contradiction to a sequence because these balls cover the whole X. So there has to be, so at least one ball has to contain infinitely many xn's. Sorry, it needs to cover xn for infinitely many n. That xn can be just a single point also for a constant sequence. But yeah, so B is true. Now for C, uh, for k naught, we can find out B naught of radius 1 over k naught such that xn is contained inside that. That is from B. We can do that. Then for any k1 which is larger than k naught, so the radius of that will be smaller. Okay, 1 over k1 will be smaller than 1 over k naught. Okay, so b1 1 over k1 will be a smaller ball. So now it says that such that the accents, such that those such that the it has infinitely many intersection points in it. Okay. So again, you apply the same similar thing uh, for this as well. Now the ball. Now you can think of the xn. Infinitely many xn are contained inside this ball b naught of 1 over k naught. Okay, infinitely many xn. And now this infinitely many xn. Now you consider another. Now you consider another cover of finitely many balls by 1 over k1 balls. So it will also cover this. Now those ball will also cover this. So there is a finite cover of finite cover of b naught 1 over k naught as well by b1 k 1 over k balls. All right. So because it contains infinitely many, so there has to be one ball from this collection that contains infinitely many points by the same logic that we gave above. All right. So the intersection will again have infinitely many points in it. Okay, for infinitely many infinitely many index points and in this. Okay, so I apply the similar logic that I applied over here over there here as well. Okay, so C is also correct. Now it says that there is a Cauchy subsequence of xn. So this is because of the argument C, option C. Okay, so what is a Cauchy sequence? Cauchy sequence is given a sequence xn is Cauchy if for a given epsilon a given epsilon reduced ball there exists a natural number n naught or n such that d of distance between xn and xm is smaller than epsilon for all n and m greater than n. So in particular, if you have a ball of some radius, let's say, so this is your 1 over k naught ball radius. So then, or 1 over epsilon radius ball, then x n and xm, their distance is going to be smaller than epsilon. Okay, in this case, it can be larger. So let's take 2 epsilon radius ball. All right. No, let us take epsilon by 2 radius ball. Now it is fine. So for epsilon by 2 radius ball, their maximum distance between any two points can be epsilon. Uh, must be smaller than epsilon. Okay, it cannot be epsilon or larger than epsilon. All right. So this is what we need to prove for any given epsilon. We need to find out n. Fine. So that we can do from option B. We know that given a radius of 1 over k naught, there exists infinitely many xn. Uh, we know that there are xn inside a ball, some ball, okay, we don't know which ball, but there exists some ball of 1 over k naught for infinitely many points. All right. So now we call these. So this new xn, let's denote it to be x prime n. So this new xn prime is a subsequence of the original xn. Okay, because this is not the whole sequence; it is partial sequence. Okay, so it is in this. We call this new xn prime to be the subsequence of the original sequence, and we claim that this new sequence is a Cauchy sequence. Okay, why? Because for 1 over k naught we can find out that they are contained inside this. So for epsilon radius we can find out there exists an n, and by option b, by b, there exists a ball of radius 2 epsilon, sorry, there exists a ball of epsilon by 2 such that the distance between x and prime and x and prime is smaller than epsilon. Okay, so you can always do that. All right, so thus there is a Cauchy sequence, and by option C, uh, within these points you can again get a smaller radius neighborhood which contains infinitely many points by option C. That will also satisfy this thing, the Cauchy condition, and then further you can go within that. So you will always find out, however small neighborhood you choose, you can always find out a sequence. You will always find out a subsequence which is part, which is contained inside that neighborhood of that particular radius. Okay, so this completes the proof. So options B, C, D are correct. All right. Any question?
So last proof, how epsilon comes.
Yeah. So epsilon is I've just taken this epsilon because you can approximate whenever you have epsilon, you can, by Archimedes principle, you can find out a natural number such that 1 over k naught is smaller than epsilon. All right, you can find out a natural number k naught such that 1 over k naught is smaller than epsilon, right? So you can now, instead of using 1 over k naught, I am using epsilon because they are comparable now. You can compare them. So if a sequence is contained inside, let's say if a sequence is contained inside infinitely many points, infinitely many n's, if this xn is contained inside a ball of 1 over k naught, then it is also contained inside the epsilon ball. That's what I meant when I use this epsilon notation. Okay, so it is a similar thing, but because in the definition of Cauchy you need to use epsilon, you can't take discrete points. Okay, it has to be continuous, it has to be array of points, it can't be a discrete set of points. So that's why you need to take epsilon, but this epsilon can be uh, yeah, it can be approximated by a 1 over k naught rational. That's what I meant when I switched the notation. I should have mentioned this, but okay. Is it clear?
So now clear.
Okay, good. Okay, now let me write down another question. Um, this question number 3 says that let X be a topological space and YD be a metric metric space denoted by Fn xy, the set of all functions from x to y, and by Cx of y denotes the set of all continuous function. Okay, I'm just write continuous in fxy, fnxy. Yeah. Then which of the following is true? So option A says C of xy in f of xy, fn of xy is closed under the point wise convergence topology. All right. Option B says that C of xy in fn of xy is closed in uniform topology, topology of uniform convergence, topology of uniform. Option C says um, f of xy is finer than, okay, on f of xy, the uniform convergence topology is finer than, right, is finer than, that means it contains the pointwise convergence topology. Okay. Option D says on fxy, the opposite. Basically, it is pointwise convergence topology is finer than the uniform convergence topology. All right. Okay. So again, I will give you a few minutes to think about this problem, and then we will discuss the solution. Yes, that is correct answer. Okay, now let us discuss this problem. So Cxy in Fnx is closed in the pointwise convergence topology. So we need to give a counter example to that. We need to say that not every pointwise convergent sequence, sorry, not every pointwise converging family of functions of continuous function uh, converges to a continuous function. Okay, pointwise converges to a point continuous function. So for that, consider this sequence of function. Um, yeah. So define this set of function from 0 comma 1 to 0 comma 1. Okay. Um, Fn. Fn is a sequence of function from 0 comma 1 to 0 comma 1, such that Fn of x is defined to be x to the power n. Okay. Now clearly you can see that f of 0, sorry, f of Fn of 1 is always 1, right? So this function, uh, so Fn at 1 converges to constant function 1. All right. But when Fn uh, is 0, it is equal to 0. And when Fn is for x in the open interval 0 comma 1, we have this function Fnx to be x to the power n. And you can see that because as n tends to infinity, this sequence, because x lies between 0 and 1, so f of xn converges to 0. So the limit, in particular, the limit of n tends to infinity of xn is 0 whenever x lies between 0 and 1. So this also sequence converges to 0 as n tends to
0
infinity.
less than or equal to x.
Okay.
X
0 less than or equal to.
less than 1.
No, I'm saying when it is x is in between the open interval 0 comma 1, uh, then it is converging to 0, right?
Yeah, yeah.
Yeah,
So
this
0
includes.
include also.
Yeah, 0 is I've written
Okay,
separately here.
so
Yeah. Yeah. So in particular, this sequence, this point, this is a point-wise convergence because at each point it is converging, so it is a point-wise convergence. And now this point-wise convergence converges to a function which is 0 and 1. It is 0 whenever your x is in this interval, close 0, open 1, and it is 1 when it is equal to 1, when x is equal to 1. All right. So, and we clearly know that this is this function f. Let's call that function to be f. So this function f is not a continuous function. All right. So if I take a sequence of a continuous function, I have taken a sequence of continuous function under the pointwise convergence. I don't get a continuous function as a limit. So C of xy is not closed under pointwise convergence topology. That's what it proves. So it is not true. Second one is true because there is a uniform limit theorem which says that if you take a sequence of continuous function under the uniform convergence, it converges to a continuous function. Okay, so so by the uniform convergence theorem, it is continuous. So this is true. And now because of this reasoning that there exists a set which is, so Cx is closed under uniform convergence topology. That means that means its complement is open in uniform convergence topology. All right. Um Yeah, and for the argument of this uniform convergence and topology between uniform convergence and pointwise convergence, which one is bigger? So we know that a uniform convergent space is always a pointwise convergent space. Okay, a uniform convergent sequence of functions is always a pointwise convergent, but not the vice versa. So uh, yeah, so the set of pointwise convergence topology is bigger than the uniform convergence topology. For the proof, again you can refer to the one of the theorem. Uh, yeah. So option, yeah. So okay. So option C is correct. Option D is not correct. Okay. Uh, yeah, because complement of C is a closed set in uniform convergence, and it is not closed in pointwise convergence. So that means the complement of C is open in uniform, but it is not open in the pointwise convergence. So that means uh, uniform convergence is finer than the pointwise convergence. Uh, because if it is uniform, if it is open in the uniform, if it is open, uh, yeah, if it is fine, if point-wise convergence was finer, then the then you cannot find out a you cannot find out open set which is open in uniform, and then so every open set in uniform will be open in point-wise, so which is not true. So uniform convergence topology is finer than point-wise convergence topology. All right. So this completes the proof of this question as well. All right. So, oh, you mentioned BD. D is wrong. C is correct. All right. Um, okay. So let's stop now. If you have any doubt in this, you can ask me. Otherwise, we can stop.
No, sir.
Okay. Good.
Thank you, sir.
Thank you for joining. Yeah. Um, yeah. This is the last session. Okay. Bye. See you.
Bye, sir. Thank you.
Yeah. Thank you for joining.